thought it was just you.
We're exploring the data right now.
Oh, who's we?
The research team.
All right. Let's get started. So today's our last class. And don't forget to submit your homeworks today. I believe the last homeworks are due at the end of the day today. So make sure to get those in. So today we are going to just do kind of a overview of all the stuff that we covered. Trying to be a little bit systematic about this. I know we covered quite a lot of material, so it'll be good to kind of look at all the techniques and see how they fit into sort of a broad framework for like things that we do in data analysis. Okay? So I think kind of at the highest level, we have sort of two categories. We've got supervised learning, and we have unsupervised learning. And if we were to kind of split all of the techniques that you could do in data analysis into like two categories, this is essentially what we would be talking about. So we're going to spend most of the time reviewing most of the supervised learning stuff that we've done over the quarter. But can anyone remind me of some of the techniques that we talked about with unsupervised learning? Like, what would this cover? And what's the difference between these two? Any ideas? Bueller? What's the difference between supervised and unsupervised learning? Yeah.
Was it that unsupervised learning is more about patterns within the explanatory variables?
Yeah.
And less of a connection to the response value?
Yes, exactly. So the big difference has a response variable. So we think of this as our y, and this has no response variable, which means that no validation possible. Okay? And can anyone recall any of the any specific techniques that we did here?
Either one?
For unsupervised learning. Yes. Great. So at a high level, we've got clustering techniques, of which k-means was one of them. Does anyone remember the other one?
Nearest neighbor?
Not quite. Hierarchical, yeah. So the hierarchical clustering. Yeah, so, sorry, what did you say again?
Nearest neighbor.
So nearest neighbor may operate in kind of a similar way qualitatively to k-means, but that's actually a supervised learning technique that we use for classification, and we'll get there in a bit. Okay, so we've got our clustering techniques, k-means, hierarchical clustering, and then there are other, well, actually, I'll add, since I know that there may be some projects working on this, like a different type of clustering technique, latent cluster analysis, which is something that's commonly done in some fields, including there are some researchers and faculty in ITS who do this very often, so I'll just kind of add that here. It's a slightly more sophisticated clustering algorithm, which lets you do things like cluster on like categorical variables, which you wouldn't really be able to do with like k-means. Okay, and then there are a couple other grouping techniques which we may have kind of briefly hinted at, but these are things like principal components analysis, or PCA, and things like factorization. We talked about PCA in the context of a principal components regression. So if you remember when we did like subset selection and regularization, the third category was dimension reduction, where you do the like extract the orthogonal variation in each set of variables to reduce the number of explanatory variables. That first part is the actual PCA, and then running the regression on an outcome is the principal components regression part of it. So we had actually talked about this in the context of supervised learning, where you take this as a first stage and then apply it into a regression. You guys can look at your notes and you can see that that first stage part of it is actually like a different sort of grouping technique that you can use as an unsupervised learning. Okay, and now we'll kind of zoom out and focus specifically at supervised learning. And I'm gonna break this down into sort of two categories. We're going to do regression and classification, which again, technically still regression. Don't let all those machine learning people fool you with their fancy lingo. Classification is still regression. But what do I mean when I say regression versus classification? What is the kind of difference that we're talking about here? Yes?
Classification generally is for like binary or group categorical variables.
Yep, exactly. So this is for continuous outcome. Oh, don't know why I'm so bad at spelling today. Outcome variables. And this is for discrete outcome variables. Okay, and we'll revisit classification in just a moment. Oop.
Alan, would you say something like a Poisson regression is classification or regression? It's discrete, but it's usually used for something that's could go up to a higher number, like 100%.
Yeah, I would still consider that classification. Yeah, it is possible to have classification types of problems with like very large number of discrete variables. But I think more importantly is like the properties of that outcome variable kind of help determine a lot of the like behind the scenes techniques and modeling aspects that you take. And so that'll be more of the sort of distinguishing feature. Okay. So this kind of breakdown is maybe a little bit more sort of arbitrary. But I'm thinking about this in terms of, let's say, linear / more linear approaches. And this kind of operates on a spectrum to sort of nonlinear approaches. And one of the ways that we kind of think about this spectrum is where we go from parametric to to semi-parametric to fully sort of non-parametric problems. Okay, and so on sort of the left-hand side of things, really at the beginning of class, what were we talking about? What was our primary modeling technique?
Mostly linear regression where
Yes.
there was no degree to the power to variables we consider.
Yep. So linear regression here. And then we started to stray into sort of more nonlinear approaches. And so can anyone think of any examples of regression models that we use for more semi-parametric?
Different functional forms like logarithmic, level log level.
Sure. Okay. Yes. Yeah, we can say something like that. So log transform. And then what would be kind of the next tier of things that we had looked at? Huh? Yeah.
Or is that further down? Because it combines them both. So
Yeah. I'm going to put it further down the chain. So what's in between here and our general additive models?
Polynomials.
Yeah, exactly. So we've got the polynomial and then the stepwise and then spline models. And then I don't know if this is quite the right order. You might even argue that GAM could be like kind of in between here because it uses pieces of both the linear regression and the spline. But okay, we'll say something like that. Yeah.
How is stepwise a type of regression when it's about a selection procedure? How is it a separate regression itself? Isn't stepwise about?
I'm not talking about. Is that what I called it? I'm not talking about stepwise selection. I'm talking about the. No, I'm sorry. It's not stepwise. Piecewise. Yeah. My bad. Good catch. I'm glad you are paying attention. All right, piecewise. This is the multiple segments of the lines. Yeah, great. And then working our way towards sort of fully non-parametric. What did we talk about? Splines are kind of more in the semi-parametric. So this is, yes, kernel regressions. kernel regression. This one I'm going to put kind of like a question mark to be maybe in between here. Okay? So generally, the thing to remember is that the kind of scale that we talk about for parametric versus non-parametric. So what is the big strength of a parametric model? Where you have parameters that...
Interpretability.
Yes, interpretability, perfect. And on the other end of the spectrum, where we don't have the ability, yes, prediction, right. And so let this scale here kind of be the determinant and the sort of context that you have in your research. Let that drive your decision about like where on this scale that you want to be, right? Because if you're thinking about inferential problems, think about causality, like you want to be more on this side. And if you are more on getting the right outcomes, you know, getting like out of sample predictions to be as accurate as possible, you're going to be operating sort of more on this end. And remember, these can help inform each other, right? Because even if you're operating in this space, if you check your model with like a GAM or something, and it turns out that the relationship between, you know, one particular variable and your outcome is like really nonlinear, then maybe the assumption about linearity is inappropriate, and that could be leading to like issues in your model. So this stuff can still act as a diagnostic tool for your linear regression. Yeah.
How is a log transform taking you away from the interpretability side? Isn't it enhancing it or even preserving the interpretability of those coefficients? Like, it depends on how they change based on if it's a log level,
So yeah.
level log.
So I would think about this more in this perspective. So if I got rid of this and we were thinking about transformations, so the question is, why do we do the transformation? Okay, because because the relationship between my explanatory variable and my outcome variable isn't linear, and so you do a transformation of your inputs to try and make it linear. And the log transformation tends to be a common one because a lot of relationships between like x and y's tend to be exponential in some way. And so logging in exponential turns it into a line. Okay, so, but there's like, you can also think of like square transformations or like cubic transformations, whatever. And doing the interpretation of like a square transformation, I would argue, is like slightly less intuitive, right? Because you have to say, as you increase by a unit squared, then it changes the outcome variable by some amount. Okay. It just so happens that there's like a convenient relationship between log level, level log, and log log that actually like you can still do kind of an easy interpretation. But generally speaking, the more you do transformations, generally speaking, if it wasn't for this like convenient little fact, it would be a little bit more complicated to interpret, right? So yeah.
Also, you know, if you try to present a log transformation to a layman, they're going to be lost.
Yeah,
And if
well,
there is those convenient relationships.
yeah. Thanks to the fact that there is the convenient, because if you that's right, you have to say, oh, as you increase a unit by like a log of 1 unit, it changes by y. That would be complicated, but because we have the shortcut where we say 1% change leads to a particular outcome, that does make it slightly easier. So, yeah, let this kind of be your guide for what model that you're picking. Okay. Let's see here. And then let me jump on over to our classification. We have kind of the same idea going from parametric to non-parametric. So what are some of the techniques that we talked about for classification? Does anyone remember? Okay, great. Logistic. So I'm going to go kind of on the same scale here. Parametric to non-parametric. We had logistic regression. What was the, does anyone remember what the sort of partner to the logistic regression is? Logistic regression assumes a type 2 error distribution for the input variables, and there's a different one that assumes a normal distribution. Does anyone remember? Well, okay, yes. Probit, yeah, is a kind of version of that. The other one that I'm thinking of is the linear discriminant analysis. This is the LDA. Yeah. And so I would kind of put all of these guys kind of in the same scale.
Isn't an LD also more suitable for multi-class
Yes,
situations?
that's right.
And the logistic is more appropriate for, relatively more appropriate compared to the LDA for its binomial 0, 1 out.
Yeah. I think in practice, these are going to be pretty similar.
Okay. But in terms of test errors, would you find, let's say if you have a let's say a binomial or a multi-class problem and you apply one or the other,
Mm-hmm.
wouldn't a more appropriate technique give you a lower test error?
Theoretically, yes, but it's going to be pretty context specific, and I think that the variation in the errors are going to be fairly similar. Maybe it's a little bit better for multi-class problems, but I would actually say the more normally distributed your input data, probably the better it is to use LDA.
Okay.
Yeah, more so than the multi-class nature of it. Okay, and we kind of jump straight into some non-parametric techniques, such as k-nearest neighbors. I was looking at you because you mentioned that earlier. K-nearest neighbors. And actually, in between this stuff was a more recent classification technique that we talked about. It's kind of more common in the machine learning world. What was that?
Neural networks?
Well, actually, so yeah, neural networks is going to be everything. So we'll get back to that in a second. It was support vector machines. Yeah. And there's a lot of flexibility that you can add into here in order to do classification. I would say this leans more towards this side than this side. You're not really doing any interpretability here. It's mainly focused on outcome prediction, right? Remember, it could draw these crazy boundaries in between, these very sort of crazy boundaries between your x1 and x2 variables denoting the classification of your outcomes. Okay. I would say almost as its own sort of separate thing, we have neural networks that operate in a generalized fashion. Oop. So neural networks that operate in a generalized fashion that can replicate pretty much everything in here depending on basically how you set up the neural network, right? And so that depends on things like your activation functions and then things like your number of hidden layers and nodes. And the way that you set it up, essentially you can force it to be linear, you can make it be super flexible, you can make it with the right activation function, you can decide whether or not you're looking at continuous outcomes or if you're looking at discrete outcomes. However, generally your neural networks are going to be sort of focused more on prediction. Oh, I shouldn't even do that. Yeah. It'll be on the scale of like parametric to non-parametric. It's going to be somewhere here. It's in the semi-parametric area, right? Because you technically do have parameters and that are actually the weights in your neural networks. So it won't be totally non-parametric. Yes?
Where would instrumental variable technique plug into all of this?
Yeah, so so that's gonna be kind of a separate, it's not really fitting into the system of like categories as we talk about, but in itself is a parameter, so it's either gonna be a parametric or semi-parametric technique. Yeah. Okay. Questions, confusions, whole crazy system. Okay. So let's then move on to going back to thinking specifically about parametric models. How do you tell whether a model is good? And kind of more specifically, how is one model compared against another? So this could be something like you have y equals beta 0 plus beta 1 x1 versus y equals alpha 0 plus alpha 1 x2. Something like that. outcome variable like there. Is really where to do that. Yeah. Of error model complexity. So what are the two Wait. K nearest neighbors.
Training set, say, as such.
Yes. Yeah. Or yeah, there's not really a way of like recalibrating, right? Because you're not actually pretty complex. We think about ways essentially that we might take for this. One that we talked about.